Hi and very good evening. My name is Muhammad Shami bin SUHAIMI and I'm going to present about Archimedes principle. Now, in theory, Archimedes principle states that a body wholly or partially submerged in fluid is buoyed up by a force which is equal in magnitude to the weight of the fluid displaced by the body. Now, for example, we can see here that a 5 kg object is fully submerged into the water and then it displaces water which has a mass of 2 kg. Now, from the principle, we can state that the buoyancy force is equal to the weight of water. And we also can see that the object experiences an apparent weight loss, which is by 2 kg. Now, how are we going to determine the density of a coin using Archimedes principle? So, as an introduction, as we know that Archimedes principle states that the buoyancy force is equal to the weight of the fluid displaced. This in return means that the object has a weight reduction when submerged, and we can say that the apparent weight loss is equal to the weight of the fluid displaced. Now, this also works the same for mass, as we are going to use a mass reading apparatus. So, in all, we can say that the apparent mass loss is equal to the mass of displaced fluid. Now, the objective of our experiment is first to use Archimedes principle to determine the density of an object. And the second one is we want to study buoyant forces as a function of submerged volume. Now, buoyant force is equal to the density times the gravity acceleration and also times the volume of the water. So the setup of our experiment is as below. You can see that we are going to use a triple beam balance, which is going to read the mass of our coin. We also use a string to suspend our coin, and we also have a beaker filled with water, and we're going to use water as our reference density. And we also have an adjustable platform so that we can move the beaker water up to fully submerge the coin. So for the methodology of our experiment, first we are going to calibrate the triple beam balance. Then second, we are going to suspend the coin using a string so that we can take the reading of the coin mass in air. Now, after we have taken the reading of coin mass in air, we are going to place a beaker with water on the adjustable platform and we are going to fully submerge the coin. Then we can get the reading of the beam balance as the apparent coin mass, which is the mass of the coin inside the water. Now we are going to remove the coin and dry it, and we also are going to clean all apparatus and dry them so we can prevent corrosion. So for calculation results, as we have the mass of the coin mass in air, we are going to minus it with the apparent coin mass, which is the coin mass inside water, and then we are going to get 0.83 grams as the apparent mass loss. Now, as we have stated earlier, the mass of displaced fluid is equal to the apparent mass loss, so we get the mass of displaced fluid as 0.3 grams. Now, as we know the water density, which is 1 gram over cubic centimeter, we are going to divide the water mass by the water density, and we are going to get the displaced water volume, which means we get 0.83 cubic centimeter. Now, as the coin is fully submerged into the water, we know that the displaced water volume is now equal to the coin volume. Therefore, we can find the density of the coin. Now, density is equal to mass over volume. So we know earlier that the mass of the coin in the air is 8.63 grams. So we divide it by 0.3 cubic centimeter that we have got just now. And then for the final answer, we get 10.39 gram over cubic centimeter as the coin density. Now, as discussion, if the volume of an object is hard to be measured, it is hard to find its density. Therefore, we can find its density using a known liquid's density as a reference, just like we have done just now. And then for the second one, the apparent mass loss by a submerged object is equal to the mass of displaced water. As we had done just now, we use the apparent mass loss and then we equal it to the mass of the displaced water to find the volume of the water itself. And then the third one, the apparent weight loss therefore is equal to the buoyancy force. So I think that's all from me. Thank you.